So in this video we will be finding out the electric field due to a thick large slab. Large means the slab is extending up to infinity. So the dimensions of slab are extending up to infinity in all the directions. But the thickness of the slab is rather more, which is, let's say, D. So if D is the thickness of the slab, and obviously as the slab is thick, so the charge in this slab will be distributed within its volume. As you can see in this pink colored block, the charge is distributed within the volume. In whole slab, the charge is similarly distributed. I have just shown it here in this cubical region or cuboidal region only, but the charge is present throughout the slab. I have a point P. I have a point P, which is, let's say, at some distance x from the central line. Central line is at distance d by 2. I have to if I have to find the electric field at this point P due to this large slab, then how will I calculate it? We know that due to a large non-conducting slab, having charge density sigma, electric field at point P is simply sigma by 2 epsilon naught. I can same way use this result in this case of a large and thick slab. What is this sigma equal to? This sigma is actually the charge per unit area. So this is the charge in 1 meter square area. So what I have done here is I have also created this cuboidal region having face area to be of 1 meter and 1 meter. I have removed a segment, or I am highlighting a segment having area 1 meter square. So this area is simply 1 meter square area. The charge within this 1 meter square area can be simply treated as sigma, because sigma is the charge in 1 meter square area. So I took this 1 meter square area of this large slab, and I'm gonna find out the charge in this 1 meter square area. Although the charge is within the complete volume of the cuboid, or but that is the surface area or the front area of this cuboidal region is simply 1 meter square. So the charge in this will be area of this cuboidal region is 1 into 1, that is 1 meter square, into depth of this or the height of this cuboidal region is d, into rho. So this is the volume into density. This will give me the charge on 1 meter square face area, which is sigma. So simply I can use this sigma in this result to calculate the electric field at this point P. So electric field at this point P will be rho d by 2 epsilon naught. Very simple. Otherwise, I could have also found the same electric field using integration. For the purpose of integration, what I need to do is simply I would have used this slab, and I should create thin strips or thin slabs like this, and we have to find electric field at this point P due to each of these thin slabs, and then integrate the result. I would have got the same result in that case also, right? So that was the case when the point P was outside, right? So let it be case first. Point P is outside the slab, right? The other case could be the point P, case 2, case second, point P is inside the slab. So if point P is inside the slab, then what will I do is I'll take the slab and I'll mark the point P inside the slab, as you can see here in this figure. So if the point P is inside the slab, as you can see, then I can consider this point to be stuck up in between two slabs, one of thickness d by 2 minus x, and the other slab is that of thickness d by 2 plus x. So I can consider that this point P is just sandwiched in between these two slabs. This is slab 1 of thickness d by 2 minus x, and the other one is other slab which is of thickness d by 2 plus x. Like this you can see. So if I want to find electric field at this point, then I can simply calculate the electric field at this point P by considering that the electric field due to the first slab will be in one direction, and due to the other slab the electric field will be into the other direction. Due to the lower slab, the electric field at this point P is in upward direction, and this electric field will be simply rho d by 2 epsilon naught. So it will be rho d by 2 plus x by 2 epsilon naught. I have just used the result that I just derived. I just missed it. I just derived, right? So, and due to this thinner slab of thickness d by 2 minus x, the electric field at this point P will be in downward direction. That will be rho d by 2 minus x by 2 epsilon naught. So the net electric field at this point P will be the vector sum of rho d by 2 plus x by 2 epsilon naught and rho d by 2 minus x by 2 epsilon naught. So the net electric field at point P will be rho by 2 epsilon naught is common, and I get here is d by 2 plus x minus d by 2 plus x, right? So what I get here is rho x by epsilon naught. So this is the net electric field at point P, which is inside the slab. Okay.